Now that we've discussed what a vector field is, we want to learn about what are called line integrals. In section 6.2, we have several learning objectives. We're going to calculate a scalar line integral along a curve, then calculate a vector line integral along an oriented curve in space. Now, a vector line integral is a line integral in a vector field, which explains why we covered vector fields first. Then we're going to use the line integral to compute the work done in moving an object along a curve in a vector field. Finally, we'll describe what's called the flux and the circulation of a vector field. Before we can start, we need to define what a line integral is, specifically a scalar line integral. Now, in Calculus 1, we defined the integral of a function of a single variable to be the limit of a Riemann sum. So the integral from a to b of f of x dx meant dividing up an interval on the x-axis into tiny segments and then calculating the height of the function at that point over that subinterval and multiplying by the width of each subinterval. Then we would take a Riemann sum and take the limit as the number of subintervals went to infinity. And this is how we define the definite integral. In other words, in Calculus 1, when we integrated a definite integral, we were integrating across a subset of the real number line from x equal a to x equal b. In a sense, then, we were integrating across a line segment, where the line segment was the segment between x equal a and x equal b. Now, in multivariable calculus, we want to extend that idea, and instead of integrating on a subset of the real number line, an interval from a to b, instead we want to integrate on a curve in either the plane or three-dimensional space. In other words, we have a curve, and instead of chopping up the interval on the x-axis, we want to chop up the curve into small segments and evaluate the function across those small segments. This is what we call a line integral. A line integral will let us integrate multivariable functions and vector fields over arbitrary curves, either in the plane or in space. There are two types of line integrals: scalar line integrals and vector line integrals. Vector line integrals are line integrals in a vector field. Scalar line integrals are not applied in a vector field. Both of these can be applied to a curve in the plane, in the xy plane, or to a curve in three-dimensional space. The difference between the scalar line integral and the vector line integral is whether or not it is being applied in a vector field. Let me share my screen and we'll get started on what a scalar line integral is. In video 2 over this section, we'll cover what a vector line integral is. Calculating line integrals requires a lot of parameterization. That makes it a good idea to go ahead and review how to parameterize a curve. Let's go ahead and remember what a parameter is and what it does. Remember that a parameter is an independent variable that x and y, or x, y, and z, depend upon. And as the parameter increases, the value of x, y, and z trace out a curve, either in the plane for x and y, or in three-dimensional space like a helix for x, y, and z. The parameter typically used is the parameter t. It can often represent time, but not always. In that sense, we could have what happens at a point in time where x is horizontal, y is this direction, and z is vertical at a particular point in time. So the parameter does not actually appear in the graph at all. It helps us graph it, but it is not a part of the graph. T does not appear on the XY plane or in XYZ space in R3. Instead, it helps us to draw the curve and gives us an orientation to the curve, a beginning place and an ending place, and a direction along the values of increasing t. Let's go ahead and review some of our more common parameterizations. We studied these quite a bit earlier at the beginning of chapter 3, and now we see them again here. We can parameterize an ellipse, x squared over a squared plus y squared over b squared equal to 1, in the counterclockwise direction by setting x to be a cosine t and y to be b sine t, and allowing t to vary from 0 to 2 pi. We can go clockwise by taking the opposite value for y, negative b sine of t, but again allowing t to vary from 0 to 2 pi. The only difference between the ellipse and the circle is that the coefficients of x and y are both the same, because in a circle, the radius is a constant. In fact, a circle is a special case of an ellipse. So to plot a circle in the counterclockwise direction, set x to be the radius times cosine t and y to be the radius times sine t. To go clockwise in the other direction, set y to be negative r sine t. In both cases, we allow t to vary from 0 to 2 pi. There are various ways of parameterizing a line segment, but one of the methods that we covered in section 3.0 was a line segment from some point x naught, y naught, z naught to x1, y1, z1. In order to parameterize it, we wrote it as a space curve, where r as a function of t is equal to 1 minus t times the initial point represented as a position vector, plus the parameter t times the second point also represented as a position vector. In other words, the x component is 1 minus t times x naught plus t times x1. The y component is 1 minus t times y naught plus t times y sub 1. And the same for z as well if we're in three-dimensional space. If we're in two-dimensional space, we would stop after the representations for x and y. This parameterizes the line segment with the parameter t going from 0 to 1. However, recall that parameterizations are not unique. There are infinitely many ways to parameterize any curve in the plane or in three-dimensional space. So this is not the only way to parameterize a line segment. In general, if we want to represent a curve, y equals some function of x, in parametric form, we can set the independent variable x to be t, and y then becomes a function of t. We can also do the reverse and represent it as a function of y, allowing y to be the parameter t and x to be a function of t. In order to continue and find out what a scalar line integral is, we're going to have to make some more definitions. Let's go ahead and start talking about what a scalar line integral is. First off, they're very similar to the definite integral for a single variable function that you've already seen in Calculus 1. The difference this time is that the integrand will have to be a function of more than one variable, either a function of two variables when the domain of the integration is a curve in the xy plane, or a function of three variables where the domain is a curve in three-dimensional space, like a helix. The question is, though, how do we integrate over a curve as opposed to integrating across a line segment on the x-axis? How indeed do we do this? We're going to chop up the curve into small pieces instead of chopping up sections of the x-axis. So visualize, if you will, that you have a curve down here. And this curve could either be in the plane or in three-dimensional space. This particular curve is represented in the plane, the xy plane. We chop it up into different pieces. So from P naught to P1, P1 to P2, P2 to P3, and so on. We're dividing this longer curve into smaller segments. And then what we want to do is we want to take some representative point in each little section of the curve, call it P sub I star, where we're going to evaluate the function. And then we're going to multiply it by the length of that particular section. In other words, each little section has an arc length. We're going to evaluate the function at a point in the ith subsection of the curve, and then we're going to multiply it by the arc length of that ith subsection. This is what we mean when we talk about a scalar line integral. We will multiply this function at that particular point by the arc length, which is delta s, and then we'll add the products of the function times the arc length up over all of the cuts that we made in the curve. Then we'll allow the distance between the points on the curve to go to 0 by taking a limit. The result is the scalar line integral of the function over the curve. In order to fully define what a scalar line integral is, we need to remind ourselves what the definition of a smooth curve is. We saw this back when we first worked with vectors. Let's remind ourselves of what a smooth curve is. A curve C in either 2 dimensions, the xy plane, or in 3 dimensions, like a helix, is considered smooth if its derivative, when represented as a scalar or as a space curve, r of t, when the derivative is continuous and not the 0 vector when written in parametric form. So we have a vector r of t, which is going to have some function of t for the first component, second component, and if it's in 3-dimensional space, the third component. And when we take the derivative of that vector, we don't get the 0 vector, and the derivative is continuous. In that case, we call it a smooth curve. Now, in 2 dimensions, r of t could be h of t in the I hat direction plus g of t in the j hat direction, or h of t, g of t. In 3-dimensional space, we would have yet another function to represent the z direction. It's smooth as long as the derivative is continuous and not the 0 vector, which means because our derivative is the derivative of each scalar valued function that is a component of the vector, that at least one of those derivatives is not 0. Let's now take a look at the definition of a line integral with respect to arc length. What we're doing is we're calculating the integral, but not along a horizontal section of the x-axis. Instead, we're calculating a line integral along a curve, which of course will, well, curve in either 2-dimensional or 3-dimensional space. We're going to let f be a function with a domain that includes a smooth curve C. So the curve has to be completely inside the domain of the function, and it has to be smooth. We're going to allow our parameterization of that curve to be x as a function of t and y as a function of t. This can also be represented as h of t and g of t. Then we define the scalar line integral of the function f as a function of x and y along the curve to be the limit of the Riemann sum from I = 1 to n of the function value at some point within each subsection of the curve multiplied by the arc length along that section of the curve. Now, we can also take this into 3-dimensional space if we allow our curve to be a 3-dimensional curve like a helix. In that case, r of t would be x of t, y of t, and z of t, where t varies between a and b. And the scalar line integral is, again, the Riemann sum of the product between the function evaluated at some point along each cut of the curve multiplied by the arc length of that curve, provided the limit exists. This is sometimes called the line integral with respect to arc length because you are differentiating along an arc, along a curve, rather than along a linear line segment. Let's talk about how we actually convert this. What we've got right here is we've got an integral of the function across the arc length differential. So we write this scalar line integral as the integral over a curve. So notice that we only have the c showing up under the single integral symbol of some function with respect to arc length. So the integral over a curve of f ds, where ds is that arc length differential that we saw earlier this semester in section 3.3 and 3.4. Now, integrating with respect to arc length can be quite difficult. When we were working in section 3.3, we converted the arc length differential into something we could actually compute, namely the magnitude of the derivative of the parameterization of the curve. Let's go ahead and let r of t be some parameterization of the curve, x of t, y of t, z of t, assuming we're in three-dimensional space, and it is a smooth curve. Since it's smooth, we know that the derivative does exist and is continuous for all t between a and b, where t goes from a to t equal b. And we also know that the derivatives exist, and at least one of these derivatives is not zero, because we know that the derivative of the parameterization is not the zero vector. Now, imagine, if you will, that you're cutting up the curve into smaller segments. And we're going to take the ith curve, the ith subsection of our curve. So let's go ahead and draw a curve and kind of represent what we're talking about. So we have a curve, and what I'm going to do is cut the curve up. And if I keep cutting the curve up all the way across, then let's say that this one right here is the ith subsection. So this is my ith cut of the curve, and the curve is produced starting on the left with t equal to a and stopping on the right with t equal to b. Now, if I'm looking at the arc length over just the ith curve, and by the arc length over the ith curve, I'm specifically talking about how long that particular arc is, then I know from what we learned in section 3.3 with the formula for arc length, that that arc length, delta s sub I, is the integral from t sub I minus 1 to t sub I of the magnitude of the derivative of the parameterization with respect to t. Now, the magnitude of a vector, of course, is the components of the vector squared, added together, and then we take the square root, which means that we can also represent it as you see on the right. Notice that this converts from being a function of ds into being a function of t. Not only that, but if we make the distance over which we're cutting small enough, then this section here, highlighted in purple, becomes smaller and smaller and more linear. Because it becomes more and more linear, we can approximate the arc length of it with the tangent vector over this particular interval. Because if it's linear, the tangent vector lays directly on the line. And as it becomes smaller, it becomes more linear. So we can say that the magnitude of the derivative of the parameterization is approximately equal to the magnitude of the derivative at a particular point in that subsection multiplied by delta t sub I. In other words, I'm going to pick a point in that little subsection, and I'm going to call that point right there my I sub I star, P sub I star. And what I want to do is I want to evaluate the parameterization at that point by letting T be T sub I star. Now, these are not exactly equal to each other because, of course, this little arc here is not exactly linear. So while it's roughly the length of the tangent vector, it's not exactly the length of the tangent vector. This is an approximation. However, what we're going to do, of course, is to add up all of the subsections on our curve by taking a Riemann sum, so that what we see on the left, which of course represents the scalar line integral as we defined it earlier to be the Riemann sum of the function at a particular point in each little cut multiplied by the arc length of that tiny section of the curve. We can approximate this with the function value at a particular point in each subsection multiplied by the length of the tangent vector over that subsection times delta t. Now you know what we're going to do, since this is calculus and we do it all the time. Once we have a Riemann sum, we take the limit as the number of cuts along the curve go to infinity. That's the same as saying that the length of each little segment goes to 0. As we take that limit, this approximation becomes an equation. That gives us the equation that you see here, that the limit as n goes to infinity of the scalar line integral definition becomes the integral from a to b of f of r of t times the magnitude of r prime of t dt. We have converted what was a line integral with the differential ds into a single integral over dt. Let's talk about evaluating. And again, this picture here is simply emphasizing that as you take smaller and smaller cuts, since it is a smooth curve, each little section becomes more and more linear, so we can approximate its arc length with the magnitude of the tangent vector over that small interval. This gives us the evaluation of a scalar line integral, the integral from over the curve C of f ds, as the integral from a to b of f of r of t times the magnitude of r prime of t dt. The integral on the right is an integral of a function of a single variable, a la calculus 1. The integral on the left is a scalar line integral where we're cutting up a curve and we're integrating along the curve with respect to the arc length. So if we have a function, r of t, or a function of two independent variables, and a smooth curve in the plane, r of t equal to x of t, y of t, then this representation of the scalar line integral becomes f of x of t, y of t times the square root of dx dt quantity squared plus dy dt quantity squared. Again, what we're doing is we're replacing the magnitude of r prime with its representation as the square of each derivative added together and taking the square root of it. We have a similar definition for a function of three independent variables and a smooth curve C given by x of t, y of t, and z of t. In that case, we get an extension of what we had the previous time, where the magnitude of the derivative of the parameterization is dx dt squared plus dy dt squared plus dz dt squared, all underneath the square root. And then we multiply by the function value at that point, x of t, y of t, and z of t. It's the value of the function multiplied by the arc length that gives us the scalar line integral. As a consequence of this theorem, we can actually think of the arc length differential ds as being the magnitude of the derivative of the parameterization times the differential dt. In other words, the change in arc length is the same as a change in t, but scaled by the magnitude of the vector r prime. Let's now talk about what it is we're actually computing. In the case of a function of two independent variables, f as a function of x and y, we do have a physical interpretation for what the scalar line integral means. When we have a function of three independent variables, we'll lose this physical definition or interpretation of what the scalar line integral is. But we do have some applications to work that will give you a sense of how it can be used for a function of three independent variables. Let's start with a function of two independent variables, f of x and y. Let's suppose that this function is just the plane f of xy equal to x plus y. So we have a slanted plane in three-dimensional space. We want to think about a curve in the xy plane. If we have a function of two independent variables, then our curve C is going to be in two dimensions. It's going to be in the xy plane. And we want to integrate over it. And it's represented by y equal x squared, where x is limited between 0 and 2. Now we know x squared, of course, is just a parabola, and saying that x goes from 0 to 2 means we're chopping off the left arm. So we have the right arm only in the xy plane. So if you look at this graph on the left, you can see the xy plane, which is typically our floor, and you can see that we've got graphed the right arm of that parabola. In fact, we've got an oriented curve where we're starting at the origin here, where t equals 0, and we're proceeding in this direction along the curve until we stop here where t equals 2. In the image on the right, we have the plane above this curve in the xy plane. So we want to know, what does that scalar line integral represent if I evaluate the scalar line integral for the plane x plus y, but specifically over that curve in the xy plane? And the answer is, it's the area of what's called a drop curtain. So the next thing we want to do is visualize taking each point on the blue half parabola and drawing a line directly up, straight up, until it touches that slanted plane. So everywhere along the curve, we're going to draw up that until it touches the slanted plane. When we do that, it creates a sort of curtain or wall. And the area of that curtain, called the drop curtain, is the value of the scalar line integral. Let's take a look at what it looks like. Here's what the scalar line integral looks like. And we can look at it out here on CalcPlot 3D. You can see if you rotate up, let me go ahead and get the Z out of it. You can see that in the XY plane, I do have the right half of an upward opening parabola, but it's only graphed between x equals 0 up to x equal 2. That's the blue curve. Now, the next question is, what is it that we're getting And let me get this back into normal orientation. And I'm going to rotate it around like this. So I have the blue curve here on the bottom in the plane. I also have a red curve right here, which connects the two. What is that red curve? The red curve is the projection of the curve from the plane onto the surface, which is the x plus y plane. So when we're looking at it, it's like drawing a curtain, like a single line between every point on the blue curve and going up until it touches that slanted plane. And then we want to find the area of this red shaded region, which is what's called a drop curtain. We can look at it from different angles, and you can see that it does go up and touch the slanted plane at that surface. So the red is the projection of the blue curve from the plane, but onto the surface itself. It is the point where when you draw up the curve, it touches the slanted plane. And we'll talk a little bit more about how we can parameterize this in CalcPlot 3D after looking at example 1. In example 1, we want to find the value of the scalar line integral across a curve C of x plus y with respect to the arc length differential ds, where C is the curve parameterized by x equal t, y equal t, for t between 0 and 1. Now, if x equals t and y is also equal to t, then basically x equals y for x between 0 and 1, which means that the graph that we have is the graph of the line y equal x, starting at the origin and moving up towards 1, 1, which you can see here on the lower left. We can parameterize this in CalcPlot 3D by setting x to be t, y to be t, and z to be equal to 0, and graphing it as a space curve. Make sure you restrict x, or t rather, to be between 0 and 1. Now we can look at this particular curve underneath our slanted plane. This is the same plane as before, just for fun, no particular reason. So this time we want to draw points, connections between here, straight up, parallel to the z-axis, until we touch that slanted plane. And that's going to create a curtain. And we want to find the area of that curtain. And the area of that curtain is the value of the scalar line integral. In a sense, this should sort of make sense, as each little subsection of the curve gives us the width of the subinterval, and the value of the function gives us the height. So we're getting width times height, or length times width, which is area of a small rectangle. And if we add all of the rectangles together, we'll get the area of that drop curtain. Let's recall that for this particular problem, we have x equal to t, y equal to t, and t between 0 and 1. Let's go ahead and take a quick look at what this looks like on CalcPlot 3D, and I'll show you what we've graphed so far. In this case, you can see up here that I've defined my curve in the plane as x equals t, y equals t, z equals 0 for t between 0 and 1. I chose to use a solid color, and I increased the thickness of the curve to a 4. You can find these by clicking on the gear symbol. When you scroll down, there's a box that says curve width. I changed mine to 4. The other thing you can do is click on use constant primary color and pick your color. Then in the box where it says orientation arrows, I chose 3. This is going to draw arrows from the smallest t value in the direction of the larger t value. This gives me the curve in the plane. And then I plotted the plane itself, x plus y, as z a function of x and y. That's all I have so far. Let's go ahead now and take a look at the next step in evaluating the scalar line integral. The next step is to represent f, which is a function of x and y, x plus y, in terms of t only. To begin with, it's a function of two independent variables. We need to make it a function of one independent variable, the variable t. Then we want to find dx dt and dy dt. We're going to start by saying that f of x and y is equal to x plus y. That much was given. That means that we can write f as a function of t by replacing x with t and y with t to represent f as a function of t as 2t. The next thing we want to do is calculate the derivative of x with respect to t, which is the derivative of t, which is just 1. dy dt in this problem, since y is t, is also 1. And then we can apply this into the formula. Let's go ahead and set up the integral now. We know our t value varies between 0 and 1, so those become the limits of integration. We want to represent f as a function of t in the next part, which is going to be, oops, I don't know why I have the equals there, 2t times, and now I need to find the magnitude of the derivative of the parameterization. dx dt is 1, so I have 1 squared plus 1 squared, which will give me the square root of 2. So my integral goes from 0 to 1, 2 square roots of 2 times t with respect to t. We can integrate this directly, and this will give us, of course, the square root of 2 times t squared evaluated between 0 and 1. And this will give us the square root of 2 square units. This represents the area of the drop curtain of this particular shape. Let's go ahead and take a look at how we might find the drop curtain. In order to find the drop curtain, we need to represent the curve, that is the projection of the curve in the plane onto the slanted function, the slanted plane. So in order to do that, we leave the parameterization for x and y the same. X is t and y is t. But the z value, instead of graphing it in the xy plane, I want it to appear on my slanted plane. So I need to set my z value to be the value of the function in terms of t. That means that I'm going to set it to be the space curve t, t, 2t. Let's take a look at what that one looks like. You can see right here that I have kept the parameterization of x and y the same. But to draw the curve on the surface itself, I represent the z component as the value of the function represented in terms of t. When I do that, you can see that it's graphed here in red. The red that you see in the curve on the slanted plane is the connection, the point coming from the blue curve straight up and touching the slanted plane. Let's go ahead and rotate it a little bit more so we can see what it looks like. When you look at it from this view, you can see that the red is definitely in the slanted plane, but directly above the curve in the XY plane. Once you have parameterized the projection of the curve in the plane onto the surface, then you can do what's called a drop curtain. Click on the gear symbol, and scroll down to animation settings. This is below where it has curve width. If we want to make the curve width larger, we could set it to be 4, and we want to click on the box that says show drop curtain to XY plane. Once we do that, we can see that we've made this projection of the two-dimensional curve onto the three-dimensional surface thicker. And we've dropped a curtain from the surface down on top of that curve in the XY plane. And what we're finding is the area of that drop curtain, which is pictured here as a black sort of triangle shape. Let's go ahead and move on to a representation that we will use more often as we progress through chapter 6. And that is, instead of working with the formula in the dx dt squared plus dy dt quantity squared under the square root form, we're going to instead parameterize it as a space curve. Since x equals t and y equals t, we can write a parameterization as t comma t in angle brackets. Then we can find the derivative of that, which becomes 1 comma 1. And then we can find the magnitude of that, which is the square root of 1 squared plus 1 squared, which gives us the square root of 2. This means that we can find the evaluation of the space curve as evaluating the function as a function of t multiplied by the magnitude of r prime with respect to dt from t equal a to t equal b. Let's take a look now at example 2. In example 2, we want to finish the original problem that we started with, which has the same surface, the slanted plane x plus y, but the curve in the xy plane down here is instead y equal x squared, but restricted to x between 0 and 2. So in other words, the right arm of an upward opening parabola. We want to compute the area of the drop curtain, which is the scalar line integral. When you look at the slanted plane, you can see it here, and the blue curve is the right arm of an upward opening parabola. We connect the curve with the surface by drawing lines parallel to the z-axis, and then we want to find the area of this red curtain. Let's take a look at the curtain again. You can see it here in this image. If we take a look at what it looks like in the XY plane, again, you can see it is the right arm of an upward opening parabola. Let's go ahead and find the area of this green drop curtain, which curves in three-dimensional space. To do that, we want to first parameterize the curve and the function. You always start with parameterizing the curve. The parameterization of the curve will affect the representation of the function in terms of t. In this case, we know that we want y equal to x squared, so we choose to let x be the parameter t and y to be t squared. We're restricting the parameterization for t, or x, to be between 0 and 2. Once we have the parameterization, which is r as a function of t, we can go ahead and find the representation of the function in terms of t. Our surface is x plus y, the slanted plane, and this dark gray. X is t and y is t squared, so that makes the function of t plus t squared. Now that we've parameterized it, and we know that t varies from 0 to 2, we want to go ahead and start writing down the value of the scalar line integral. To complete it, we know that our a is 0, our b is 2, our function is t plus t squared, but we need to compute the magnitude of the derivative of the parameterization. Our parameterization is t, comma, t squared. If we take the derivative of it, then we get 1, comma, 2t. Once we have the derivative, we want to find the magnitude of it by computing the magnitude of the derivative of the parameterization by squaring each component, adding them together, and taking the square root. This is going to give me the square root of 1 plus 4t squared. And the next thing we're going to do to convert the differential ds into a differential with respect to t is scale it by this particular factor multiplied by dt. So our integral then becomes the integral from 0 to 2 of the function t plus t squared multiplied by the square root of 1 plus 4t squared dt. Now, this is a rather more complicated integral to compute, so I recommend that you go ahead and use an online integral calculator to find it, and then turn the video back on and we'll compare our results. In this case, I would simply substitute the integral into an online integral calculator, and you get the result 167 divided by 48 times the square root of 17, minus 1/12, minus 1/64 of the natural log of the quantity 4 plus square root of 17. A pretty complicated answer, which turns out to be about 14.2 square units. And again, what we're calculating is the area of that drop curtain. Now, what if we had a function of 3 or more independent variables? We can still calculate the value of the scalar line integral, but we lose that connection with the area of the drop curtain. However, there are lots of applications in engineering and science that use such integrals. For example, we can use the scalar line integral to compute the mass of a wire from its density function, where the wire is either in 3 dimensions, like a helix, or in 2 dimensions. Let's now look at some of these applications of scalar line integrals, starting with the mass of a wire. If we let the density function for a wire be given by a function of either 3 independent variables or 2 independent variables, and we let the wire be parameterized by the smooth curve C, represented by the space curve R of t, then the mass of the wire is the scalar line integral of the integral over the curve of f ds, which gives us the integral with respect to t from a to b of f of r of t times the magnitude of r prime of t. In other words, just the scalar line integral as we've been doing previously. Let's take a look at example 3. In example 3, we're going to consider a slinky, which is more or less a 3-dimensional helix shape. We're going to consider the wire of the slinky to be infinitely thin. Let's suppose that the shape of the slinky, this helix in 3-dimensional space, is given by r of t equal to sine of 3t cosine of 3t times t. And t varies from 0 to pi divided by 4. We also want to allow a function of 3 independent variables, x, y, and z, to represent the density at any point along the slinky given by the function x squared plus y squared plus z. We want to find the mass of the slinky by calculating the scalar line integral with respect to ds. In this case, the curve is the slinky itself. Go ahead and pause the video to work this one out, then turn the video back on and we'll compare our result. To represent the scalar line integral over the curve of the function x squared plus y squared plus z with respect to the arc length differential ds, we need to represent f as a function of r and t and multiply by the magnitude of r prime of t and integrate from t equals 0 to t equal pi over 4. We're given that the parameterization is sine of 3t, cosine of 3t, and t. That makes x as a function of t, sine of 3t, y as a function of t as cosine of 3t, and z as a function of t of simply t. Then we need to compute the derivative of the parameterization r prime. This gives us the vector 3 cosine of 3t minus 3 sine of 3t, comma 1. This is a vector valued function which represents the derivative of the parameterization. To find its magnitude, we square each component and add them together, then take the square root. This gives us a trig identity under the radical of 9 times the quantity cosine squared of 3t plus sine squared of 3t, which gives us a 9 plus the 1 coming from the third component. That gives us the square root of 10 for the magnitude of the derivative of the parameterization. Next, we need to represent our function in terms of this parameterization. We're given what x, y, and z represent by the components of the parameterization. Our function is x squared plus y squared plus z. So we replace x with sine of 3t, y with cosine of 3t, and z with t. This gives us another Pythagorean trig identity. Sine squared of 3t plus cosine squared of 3t is 1 plus the t, which gives us the representation of the function in terms of the parameterization, or in terms of t, as 1 plus t. Now we're ready to replace each of these factors with its representation. We replace f of r of t with 1 plus t, and we replace the magnitude of r prime of t with the square root of 10. This is a very straightforward integral of a function of a single variable t. We get the result pi over 4 times square root of 10 minus the square root of 10 times pi squared divided by 32. This represents the mass of that particular wire in three-dimensional space. This is the mass of our slinky. There's one more application we want to take a look at before we end this video, and that's using the integrand as a positive 1 to compute the arc length of a curve, which we've already done once. So this is simply a repetition and a reminder of how to compute the arc length. We've set the integral, the function, to be 1, and we multiply by the magnitude of the derivative of the parameterization, r prime of t. This will compute the arc length of that curve. Let's use that to find the length of a wire with a parameterization given by r of t equal to 3t plus 1, comma, 4 minus 2t, comma, 5 plus 2t, where t varies from 0 to 4. In order to do this, we need to first find r prime of t and find its magnitude. Then we will integrate. Go ahead and pause the video to work it out, then turn the video back on so we can work it together. In order to compute the arc length, we allow our function of multiple variables to be the integrand plus 1. Then we have to compute the magnitude of the derivative of the parameterization. R of t is given above, and the derivative of it turns out to be the vector 3, -2, 2. To find the magnitude, we square each component and add them together, then take the square root to get the square root of 17. To find the arc length, we go ahead and integrate with the integrand of 1 multiplied by the magnitude of r prime. This gives us square root of 17 dt from t equals 0 to 4. This just gives us square root of 17 times 4 units. This is how long that particular wire is. Let's take a look at what it looks like out on CalcPlot 3D so we have an idea of what it is we've actually computed. When we're looking at this one, what we have is what appears to be a line segment in three-dimensional space. And what we've found is the length of that line segment. There are other applications that you can use with the scalar line integral. For example, you can find the electric potential of a charged wire given a linear charge density. This is the end of this video on scalar line integrals. And the next video over section 6.2, we'll take a look at what are called vector line integrals, where we compute a line integral in a vector field. I hope you'll join me for the next video in this series.